Hello everyone. The topic for today's discussion is portfolio construction. We shall be considering the theory first, and then there will be the application part where we shall be using the Excel to show how the portfolio may be constructed using the financial time series data. So there will be three parts for this lecture video. The first part will be considering the theory, and the two other parts will be considering the construction of portfolio using the data. The standard portfolio construction theory recognizes that different types of financial assets have unique risk and return portfolios. These make them respond differently to different economic events and different phases of business cycles. The idea of combining such various asset classes is the basis for building a diversified portfolio. Therefore, a diversified portfolio will have assets from different classes, and each asset will be coming with different or distinct attributes. A rational and a risk-averse investor's best choice, however, is always a portfolio that is constituted of less risky assets but that provide a high return. In reality, such a perfect portfolio is very difficult, if not impossible, to construct. Therefore, the issue that bothers a risk-averse investor is how to pick up a portfolio that replicates or closely resembles the perfect portfolio. In selecting a perfect portfolio, however, the consideration of risk-return portfolio of financial asset is not sufficient. We should follow the basic rule that we should not put all the eggs in one basket. That is, we should not put all the wealth in a particular asset. Therefore, we can reduce the investment risk by combining more than one stock or more than one asset. The risk in a portfolio of diversified individual stocks will be less than the risk inherent in holding any one of the individual stocks. So here we are assuming that the risks of the various stocks are not positively correlated. So if we are going for any effective investment, then that does not mean either picking or combining stocks at random. So the rule of the game is to find out the right basket to keep the eggs. So it is the combination of stocks that matters. We shall have to find out the particular way or the particular combination in which the different stocks may be combined. Now we come to the concept of risk. The standard portfolio theory suggests that the risk associated with individual stocks could be decomposed into two. The first one is the non-diversifiable market or systematic risk, and the second one is the unsystematic or the unique risk. This risk is specific to an individual stock, and it can be diversified away by increasing the number of stocks in a portfolio. The market risk or the systematic risk, however, cannot be diversified. For a well-diversified portfolio, thus the individual stock risks add very little to the portfolio risk. Instead, it is the market risk that matters, or it is the correlation between the individual stock's return that determines overall portfolio risk. Now, construction of an efficient portfolio is a standard mean variance optimization problem. It starts by assuming that number one, the investors who participate in the market are risk averse, and secondly, their preferences are represented by a derived expected utility function which is defined over the mean and variance of a portfolio's return. Now this mean is M and variance is S square. The standard assumption on such preference relationship is that the investors are induced to prefer higher means and smaller variances, and this variance measures the risk. Under this assumption, the optimum portfolio for risk-averse investors are those that provide highest expected return for a given level of variance or a given level of risk, or alternatively, those with the smallest variance for a given level of expected return. Now, such portfolios are called mean variance efficient portfolios. We should be working with a broader class of portfolios that are called the minimum variance portfolios. Now, what are the minimum variance portfolio? Minimum variance portfolio gives the smallest variance at every level of expected return. So, as is obvious, all mean variance efficient portfolios are minimum variance portfolios. The mean variance analysis is consistent with the expected utility maximization. In general, all the minimum variance portfolios are included in the optimal set. Now we are making some assumptions. Number one, each individual is choosing a portfolio to maximize a derived concave utility function of the form V of M S square, where M is the mean and S square is the variance. Since the utility function is concave, we have V1 greater than 0 and V2 less than 0. So V1 and V2 are the first order and the second order derivatives. Secondly, all investors have a common time horizon and they have homogeneous perception about the mean M and sigma, which is the variance covariance matrix. Thirdly, each asset is infinitely divisible. And fourthly, there is a riskless asset that could be bought or sold without any restriction. So this riskless asset may be government bond, it may be treasury bill or anything of the kind. So under all these assumptions, each investors will hold a minimum variance portfolio. No other portfolio could be optimum because given that V2 is less than 0, the minimum variance portfolio with the same expected return would be preferred to any other alternative. Now we may consider the risk and return on the N asset portfolio. So we consider N assets where Ri is the return on the ith asset. Ri is calculated as log of Pt by Pt minus 1. Now there is an alternative formula. We can also use Pt minus 1 by Pt minus 1, that is the proportionate change. Sigma I is the standard deviation of return, and Xi, capital Xi, is the proportion of wealth invested in the ith asset. So if we assume that the total wealth of an individual is W and small xi is the amount of wealth put in the ith asset, then capital Xi will be small xi by W. Therefore, the return on the portfolio is then given as the RPF, which is nothing but the product of the two matrices. The first matrix is the weight matrix and the second matrix is the return matrix. So for the n asset case, it is x1 r1 plus x2 r2 plus etc. plus up to xn rn. Similarly, we can find out the expected return on the portfolio following equation 2. So it turns out to be x1 mu1 plus x2 mu2 plus etc. plus xn mu n. Similarly, we can find out the variance covariance matrix of return. The diagonal terms will be giving us the variance of the individual asset returns. So var R1 is the variance of the return of the first asset. So similarly, var Rn will be the return of the standard variance of the return of the nth asset. So covariance, say R12 is the covariance of the return of the first asset and between the return of the second asset. So this variance covariance matrix is symmetric. So these off diagonal terms are equal. So covariance of R21 will be equal to covariance of R12. Therefore, sigma is equal to sigma transpose. So similarly, we can find out the variance of the portfolio, which is X transpose sigma X, where X transpose is the given matrix x1, x2, xn, the row matrix. Sigma is the variance covariance matrix and X is our weight matrix in the column form. Therefore, the variance becomes x1 square sigma 1 square plus etc. plus up to xn square sigma n square plus the covariance terms. So given this, we can find out the global minimum variance portfolio. Now in choosing a global minimum variance portfolio, the risk-averse investor allocates his or her wealth among the available assets in such a way that it will minimize the risk of investment. So in other words, he or she will choose the weights given to different assets in a portfolio so as to make the variance of the chosen portfolio the minimum possible. Therefore, the choice of the minimum variance portfolio is basically a choice of weights given to the available assets. So, the constraint minimization problem is given as minimizing sigma square PF, which is the x1 square sigma 1 square plus etc. plus sigma n square xn square plus the covariance terms, subject to the constraint that sum of all the weights should be equal to 1. So we can set the Lagrangian function for the problem as like this. Then the first order conditions are given So solving this, we can find out the weights. Now in matrix notation, the minimum variance portfolio choice problem turns out to be minimize the portfolio variance, which is equal to x transpose sigma x subject to x transpose 1 is equal to 1. The first order conditions are described as is given in the matrix format. So this is turning out to be 2 sigma 1 1 0 into x lambda matrix, and that is equal to the 0 by 0 1 matrix. Now this is of the form Ax Zx is equal to b, and the solution for Zx will be given by Ax inverse into b. So solving, we can get the optimal weights that will help us construct the global minimum variance portfolio. Now we shall see how to construct the portfolio in Excel format using a financial time series data. The analysis will be done in two parts. In the first part, we shall be considering the construction of the efficiency frontier and the market portfolio. And in the second part, we shall be talking about the construction of a minimum variance portfolio.